Here we're going to take a look at some examples of max and min problems from mathematics. No new definitions, no new rules. Here's an example. Find two numbers whose sum is 20 and whose product is as large as possible. So here's what we want to do. We want to find a product that's as large as possible. I like to make a note that says we want to maximize something here. We want to max. And what is it we want to max? A product. So I'm going to call that P, and that's what I'll use to name my function. So I know that my two numbers add up to 20. So let's call those two numbers, say, X and Y. So if I want to max their product, the product is X times Y. Now, there's a bit of an issue here with moving forward because this is a function in two variables and I really need it to be written in one variable before I take the derivative and find critical numbers. So I also know this other piece of information, that the two numbers sum to 20. So I can write X plus Y equals 20, and I can solve this equation, sometimes called the constraint, and use that to substitute back into my objective function. I'll write that over here, sometimes called the objective, the function that we're trying to optimize. So how about we do this? I know that X plus Y equals 20 implies that Y is equal to 20 minus X. So let's sub that in. Now I have the product function as X, not times Y, but times 20 minus X. And that means that this function can be written as 20X minus X squared. Step 2, we want to find the critical value. That's where a maximum or minimum is going to be. So let's move forward. P prime is 20 minus 2X. And if we set that equal to 0, we'll see real quick that X is equal to 10. So one of the numbers is 10. The other number can be found by taking that 10 back into the constraint. Y equals 20 minus 10. Replace the X with a 10. And now we have Y equals 10. So what are those two numbers? The two numbers are 10 and 10. And what's the product? The product is 100. So there's that. I did want to take a look at this function, though, graphed, because I think there's some good information to see. Let's take a look at this function. This product function, which we can use in our graphing calculator as y1, and it's equal to x times 20 minus x. So here's our calculator. Y1 equals x times 20 minus x. And let's hit enter and see what this graph looks like. Oh, there's almost nothing there to see. So let's zoom out until we have a better idea what's happening. So we'll zoom out a little bit. I can kind of start to see a little bit more information here. And I believe that this x value to the far right is going to be 20 because the two numbers have to add to 20. So it makes sense then that one could be 20, the other could be 0. All the way up at the top, though, there's the maximum value. So let's change the window just a bit. Let's make our x minimum -1. Let's make our x maximum 20. Let's call it 21 so we can see the x-intercept. And then let's make the y minimum -1. We just need to be able to see the axis. And how about the y max? Since we know the max product is 100, I'll go all the way up to 110 here, maybe 110. And let's take a look at that graph. There we have it. So all the way at the top of this graph is the maximum value, and to the left and right, those endpoints represent 0 and 20. But we see the max product is found when one number is 10 and the other is 10. So let's go back and do a different question. This one is exercise 1 from your text. We'll save that for class. And next, we have more of a graphical problem. A rectangle is to be inscribed under one arch of the sine curve. What is the largest area that the rectangle can have? And give the dimension, or what dimensions give that area. So here's the sine curve. That's the one in blue. I'm going to call it y equals the sine of x. And there is a rectangle drawn underneath this arch. And so let's label a point, maybe right here. Let's call this point x, y. So that means that this is a length of y, and this is a length of x. So let's get to the optimization. What's the largest area the rectangle can have? So what we want to do here is maximize the area of the rectangle. So my objective is to max an area. So we need now an expression for the area of the red box or rectangle underneath the sine curve. Well, we know that the area of a rectangle is base times height. I know the height of the rectangle is y. That's not a problem there. It's the base or length of the rectangle that's an issue. But I think we can grab that. We know that the entire length from the start of the curve above the x-axis to the end is pi. And if we know that this section is x, then that implies that this section is x as well. So the part left over, the length of the rectangle, is going to be pi, that whole base, minus 2x's. This is pi minus 2x. So that means the area is pi minus 2x times the height, y. So that's in two variables like example 1 was, but we also know as a constraint that y is equal to sine of x. We know that from the graph of the sine curve there. So we can replace y with what it's equal to, sine of x. So that makes the objective function a for area equals pi minus 2x times sine of x. All right, we've got our objective. It's written in one variable. Let's differentiate. So a prime is equal to, and we can use the product rule here. So the first function will be pi minus 2x times the derivative of the second, so cosine x, and then plus the second function, sine of x, times the derivative of the first function, which we can call, well, derivative of pi is 0, derivative of negative 2x is negative 2. So this whole thing together is a pi minus 2x times cosine x minus 2 sine x. Now, finding the critical values of this function is not something we can do analytically. Notice that we'd have a pi cosine x and a 2x cosine x and a 2 sine x, and solving for x would be almost an impossibility, but we can use our calculator to do just this. So let's pull our calculator back up. Let's hit our y equals screen, and let's graph that derivative. So that function again is pi minus 2x cosine x. So let's see, we want pi minus 2x times the cosine of x. Make sure you're in radian mode like my calculator is here. And then minus 2 sine of x, minus 2 sine x. Now keep in mind, we'd like to know where this is equal to 0. So if we graph the function and find the 0 of the function, also known as its x-intercept or root, we'll have the x value that we want for the critical number. So let's go to Zoom and see if we can find, let's try Zoom Trig to start, option 7. Interesting. So this is not as enlightening as we would like for it to be because there are a lot of x-intercepts here. So let's go back to the graph and see which of those makes sense. Notice that our xy value occurs somewhere between 0 and pi over 2. 0 and actually all the way over to pi. It occurs somewhere between 0 and pi. So let's go back to our calculator and maybe change that window a little bit so that our x-min is 0 and our x-max is pi, and maybe this will help out a little. Turns out that there are two places here. The middle is pi over 2, and we're interested in the x value from our graph here that occurs before pi over 2. So back to our curve, and we can let our calculator find that value by hitting second calc. And then we want number 2 for the 0. And we're going to be asked two questions, a left bound, a right bound, and a guess. So for my left bound, I'm going to arrow over until we are just to the left of that x-intercept. That should work. And then we're going to arrow over to the right till we're to the right of that x-intercept, and then back over, and we're going to give it a guess. There we have it. So I'm going to go with 0.710 as my x value. X equals 0.710. And then for the y value, we just need sine of x, so sine of that x value. So let's do sine of 0.710 back to home. Sine of 0.710, hit enter. 0.652, y equals 0.652. So there are the x and y values. Those are the dimensions that give us the max area. Let's find the max area. We remember that the area is pi minus 2x times y. So pi minus 2x times y, let's see. It's going to be pi minus 2 times the x value, 0.710, times y, which was 0.652, and we hit enter, and we've got 1.122 as the max area. Max area was, let's see that one more time, 1.122. 1.122. So there we have it. There are the x values and the maximum area. Exercise 5 is a very similar question, but this time we're looking at a rectangle inscribed in an isosceles right triangle. Your hint here is it's going to help you to come up with an equation for this line. Y is equal to, what would the equation of that line be? Everything else follows pretty smoothly, and that does it for this video.